Okay, I think it's okay. It's good. Okay. So, let's see. That's good. All right. So, howdy everybody, or howdy JP, because there's only one person right now, but yeah. So I have this presentation will be about PA3. It's going to be a quick one because I just want to spend more time with the code, or more like I want you to, people to ask more questions. So this one is going to be real quick, but I hope it provides some information about PA3 beside the already provided information from the Canvas. So here's a little meme about it, but basically when people think about multi-threading programming, this one I stole from Reddit, of course. But it's basically this is yours that people think when they program it, and this is the perfect example where everything's coordinated nicely, and this is how threads start conflicting with each other and start getting you know conflicting resources and get a hang of things. So um, it's just the reality. It's multi-threading programming. It's quite complicated at first, but at the end of the day, it's just trying to coordinate multiple threads together to run to run things in parallel. So yeah. So any question for me so far? Like just a quick question, any general question? Okay. Okay, no question. It's okay if you don't have it right now. Maybe you have it later, that's fine. So PA3 will be threading and synchronization. So actually, I should not include this one in because this one is actually from the previous semester. So sorry about that. So we're going to start with the bounded buffer. So you can see that this is the overall structure of the program, where you have a bunch of patient thread, putting things into the request buffer, and then a bunch of worker popping from it to request patient data from the server, and then they would put that data that they received into the response buffer. Actually, beside just the response of data from the server, they will also tag in the patient number with each data value, so that when the histogram thread pop, they know what data is go with what patient to display on the histogram. So that will be something that I will show you more in a bit. So the bounded buffer. So when you do something like this, you want to make sure that you have many threads and you have many workers, and let's say it's called a bounded buffer because let's say there's a certain a finite amount of space that the patient thread, like P patient thread, can push in, and they're finite before the patient thread should stop pushing things. So let's say you have 10 space in the request buffer, but you have 20 threads, patient threads. That means if there's no worker to pop it from yet, then you want to make sure that only 10 threads has pushed data in, because when the 11th one pushed in, it should not be able to, else it would cause an overflow of the request buffer, and that wouldn't be good. Another problem is now the opposite side. When the worker start popping threads, right? Start popping data values, or request values. You want to make sure they don't over pop it, because let's say you have 20 threads and 20 worker threads, and you have only 10 data available to pop, well, then if the 11th worker pops, that wouldn't be good either, right? So that's something to keep about. Sorry, one thing might something coming. Sorry about that. So somebody comes in. But anyway, come back to this thing. Is that you pop in and then now you have a bunch of worker threads, and you don't want the 11th worker to pop because that would cause an underflow. Now you have too many pops, and that wouldn't be good. So that's what your bounded buffer should be able to handle, actually. So you can see right here that I reiterate again is that if there's one slot left and there's two threads can push at the same time, that would cause an underflow. If there is one data left, two threads can pop at the same time. With this is without any synchronization, and that would cause an underflow. So the goals is to lock the threads until there is enough sufficient space to push, or there's sufficient space to pop, data to pop. And to prevent underflow and data conflict caused by popping and pushing the data at the same time. Another thing you can think about is, let's say if there's one single data and two threads try to pop it at the same time, then without synchronization, two of them would get the same data, and that would also cause problem. So you want to make sure there's no duplicate, there's no underflow, and there's no overflow. So to make a lock system, and this is what you will actually put in your .h, the synchronization needed to put into the bounded buffer .h, is you need one mutex for locking and unlocking. Lock is when it has the permission. Lock is when it has the in this case referring to the thread has the permission to execute the critical section. Unlock is when it's done with execution and allows other threads to proceed. One condition variable for blocking threads from pushing, and one condition variable blocking threads from popping to prevent underflow and to prevent overflow. So I think it's good that maybe a visualization right here, and let's say, so this is actually what the vector, this is literally what's in your bounded buffer, and it's going to be something like this. So you have a bounded buffer, okay, and then you would so each of them, each spot will be a vector of car. So it's a string basically, but the reason we do vector of car like this is so it's easier to push a pop, and it's easier to get to convert things, because you don't want a string. String wouldn't work, and a vector of car versus an array of car, then a vector will be superior, because you can push and pop each character fine, just fine. So you have a queue right here. So what's going to happen is, if there's a worker, if there's a patient thread and there's a worker, then if you push, so if there's P1 and P2, P0 and P1 right here, worker was 0 and a worker 1. So let's say whenever you lock, you push, you only allow one thread to push. So one thread to push in right here, 0, push in P0 data, and then worker 0, and then P1, then it would allow P1 to pop, to push, so P0, P1 data. And then here, worker 0 would then allow worker 0 to pop. So now worker 0 can pop the patient data 0, and worker 1 can pop patient data 1. Or yeah, P1 data. So that, you know, if this one, if this one pop, this one cannot pop, because then it would not get a duplicate of P0D, because that would cause problem. So once worker 0 pop P0D, this one is gone. So then if the worker 1 can pop P1D, so that, you know, it guarantees that there's only a single copy of things during each data transfer, or in patient request patient data. Okay. So, and the same happened if let's say you have P1, P2, P3, P4, P5, let's say something like that, and then worker 2, worker 3, worker 4, worker 5. So that means this one will get like, you know, 2, 3, 4, something like this. The same. Then once you pop this, all this push in, right? Then P5 should not be able to push anything in, because, you know, there's out of space. And then the same thing happened with here. So that's why you have the condition variable, so that only 5 threads can push at the same time. So that and there are only 5 workers can pop at the same time, or the amount of worker needed for this, so that there's only a certain guaranteed amount, instead of having, so P5 should just sleep and wait until the next slot available, and worker 5 would just sleep until the next data available. So that's why the bounded buffer would resolve the whole problem with the resource conflict. So if you look at the bounded buffer.cpp, you'll see the details are how to implement. And actually, you see that they are comments for you. There are comments for you so that you can follow along. So the first comment is convert the incoming byte sequence given by message to size of vector car. So you comment in, then you can, I think there's a way you can do that. Let me see. Yeah. You just convert basically the message and the size into a vector of car. And I think, let me open up Visual Studio Code. I think it will show you. While waiting for it to open. Okay, so then I will come back to this in a bit. Wait until there's room in the next queue. So the queue length is less than the cap, so you will see that there's a cap. So that is the maximum size of the message queue. Of the bounded buffer. So there will be a unique lock. So there will be a mutex right here. And so you need to use a unique lock mutex, and then you would plug that into the waits function. So there will be in your condition variable, there's condition variable dot wait, and that would check if the lock to whether lock or unlock a thread by having a cap check right here. So a cap check, all it does is check if the current the amount of cap check would just return true or false whether there's room in the queue. So it should be a lambda function, and actually I will show you what it looks like. Yeah, I think it's fine. Actually, I don't know if that's a good idea to show you this, because I don't think it's a good idea, because that will show you the entire code. But as you can see, because I'm so afraid to show you because it's so simple. The whole bounded buffer is like 5 lines, 6 lines for the push. So basically it should be a lambda function. And if you actually hover over the wait function, or if you look it up, condition variable wait, it will tell you to plug in a lambda function. and then you can look up how the syntax of a lambda function in C++. It's actually really simple. And if you don't know what a lambda function is, it's basically a function with no name that you can quickly define within a region, so that you don't have to declare a brand new function outside with name and stuff. You could just declare it quickly within the parameter space. It's really quick. And the only thing that this lambda function does is it just return true or false if there's room in the queue left. So if the function returned true, that means, so it's a let's say if I paint this, that would probably be better. Sorry. So I think it's like if Q size, if Q dot size is less than cap, right? So cap is the parameter given to you, the user given to the program. Then Q dot size, if Q dot size is less than cap, if this is true, right, then the wait would just allow unlock, so that another thread can comes in and start pushing data. If it returned false, then the thread continued to sleep, so it blocked new thread from coming in, so that there won't cause an overflow. So false would just sit there, so that if it returned false, if cap check returns false, then wait keep blocking, then unique block keep blocking new thread from coming in until there's enough space to in the queue, so that the function the thread can come in, and then push the vector at the end of the queue. At the end of the queue to the end of the queue. Why did I say at the end? To the end of the queue, and then make sure to unlock manually before notifying to prevent waking up. So basically, so you push, so there will be like five steps. So you convert, you wait, you push the vector to the end of the queue, make sure to unlock. So you do unique lock, then you do, I think, block, and then you do unlock. Lock, and then you do unlock. You do lock, you wait, then you do unlock. Yes, yeah. So you lock, you wait, you wait. If the wait proceed, then you push, then you unlock, and then you notify. So once that you're done with your critical section, when you're done with the lock, right? You lock, because only one function can push at the same. Only one thread can push at once. So notice once you unlock, you have to notify one thread to wake up, one random thread to wake up, or you can notify all the threads. You can look up the difference about this one. Actually, this is my part, actually, because I'm not 100% sure for this particular assignment if there's a difference between notify one or notify all. I don't think there is, but it's just something to look it up. So now we talk about the mutex and the condition variables, actually. So this is a very simple example. Let's say, remember, the cap is 1. So I always think about this as like getting the money out of the ATM. So you have a room right here, a private room right here, and you have the ATM. So Alice would come in. If without the condition variable, or without mutex the condition variable, what would happen is that both Alice and Bob has the same idea of going to ATM at the same time. So they both would jump into the ATM to get the money, and that wouldn't bode well. So what you have to do instead is, now you have the condition variable, which is the cap, maximum number of people can get into the ATM room. In this case, there can only be one. And then the light right here, would notifying, so like both Bob and Alice can see that the light right here would tell that, hey, this room is blocked or not. So if Alice comes in, right? Let's say if Alice comes in, she would lock the door. This light would turn red. The cap would reduce to 0. That means Bob would have to wait outside, waiting for this light to be green green again. So it would notify him to be able to enter the room. So Alice comes in, she would lock the door, cap go to 0. This turn red. That means the Bob would have to wait outside. Once Alice done with her getting money from the ATM, then she would unlock the door. Cap would unlock the door, go out. Light would turn green. Cap would go up to 1 again. Then at that moment, Bobkin comes in and do this exact same thing, and does the exact same thing. In this case, get the money, lock the door, cap code is 0, get the money, and then get out. So yeah, so I hope that analogy makes sense. Just simple getting in the door, lock the door, which is the mutex, and then condition variable would be the cap. Yep. So so once you can do the push, pop is pretty much the same, actually. I don't think there's a difference. I think the only difference is that you have to do assertion or something like that, or you have to return. Oh yeah, you have to return the data, or return the size of the data that you pop, so that the length of the data. And that's it. Any question at this point? Or does that make sense? Yes. Okay. It makes sense. Okay. 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 I'm glad. Okay. Okay. So the last part is I'm gonna go through a step-by-step guide to PA3. Well, I'm not gonna go through the code. That would be kind of weird. But I would go through like all the details that you need to be able to implement things, and all the little details that you might need, because I think this is the most important part. I claim that this PA is the most challenging one, which from the past experience and the past classes, it seems to be the case. It used to be PA2 would be also very hard with all the parser. You have to write it yourself, but now you don't have to write the parser anymore. So PA2 became pretty easy. So now PA3 is definitely the hardest one. There's other PAs, but for this particular summer, there's only one. There's only 4. So the last one wouldn't be that hard. Actually, the last one wouldn't be that hard compared to PA3. So this one is definitely the hardest one. So but I think that the reason why people had trouble in the past is that they didn't really understand what exactly to implement or what to keep in mind when they implement things. So that's why I tried this new one where I would go through every single details, and then you would keep in mind things as you go along to implement. So things to do for PA3. So as I mentioned before, in the bounded buffer, you would add the mutex and the condition variables. So there will be one mutex for locking threads, and 2 condition variables to keep track of push and pop. So the 2 condition variable would be the slot available and data available. So that if there's slot available, then you can think of it as a number, the number of slot available and the number of data available. So that if they decrease to 0, then no new thread can come in and pop or push the data. To prevent things. Complete all the steps laid out in the cpp.cpp file. Everything is laid out for you, fortunately, so you don't have to think like, oh, what is the specific implementation here? And I think also LE4 helped you with this. Actually, I lied. I don't really even know what's in LE4, but yeah. So once you do the bound buffer, then you just type you just make test and then test. There will be four tests for just the bounded buffer. You don't need to implement anything in the client.cpp function, because actually Zeke, the guy who wrote the test, did it exceptionally well. Is that he would copy your bounded buffer into the test file and then go through the tester. The tester, you can look at it for free. It doesn't really give you anything, give away any code, but it's so that you can test the bounded buffer without having any code inside the client.cpp. So that's something. So once you do the bounded buffer, you can test, make sure it works just by doing make test without doing anything in the client. Okay, so now you come to threads functions. I'll go to threads. But if you go and let me open it up. And let's go to template. I mean, not template. Templates. Okay, so if you go to let's say client.cpp, you see all these four functions right here that you have to implement, and then so all of them are laid out for you nicely, and then you'll have the same thing down here where it tells you exactly where to implement things. You don't have to implement any of these. Maybe you would have to add a vector of channels here, because there will be each worker will have its own channel, and then if that's the case, then you need to be able to create the channels. But basically that's it. So you need to make a vector of channels here, and then you would create all the threads here, join all of them here, and then you would have to implement all this. There's nowhere else. I don't think there's anywhere else besides client, and there's only client, bounded buffer, and bounded buffer.cpp and bounded buffer.h and client.cpp that you need to implement. You don't need to implement anything else. So that makes things a little bit easier to navigate. Thread functions. So the patient thread function, all you do is you push data message to the request buffer. That's it. So you would generate data. You remember in PA1, you would generate data message, and then you would send it to server, and then you receive it immediately. In this case, the patient thread would just do the push, would just do the data message generation, and it would just push it to the request buffer so that the worker could pop it and pop it, send it to the server, receive the data, tag the patient number into each data value, and then push it into the response buffer so that the histogram buffer can pop it and then display it to the histogram. So the file thread function would generate file requests again. In PA1, you have a single process, right? A single thread and a single process. So that would mean that it would generate the request message, request messages, and then push them. I don't know why today English so much. Generate file request messages and then push them to the request buffer, and then you would immediately request buffer. So it's like an extra step. In this case, file thread function would just push it to the request buffer. All in PA1, you would generate the message and immediately get the data, send it to the server, so the server send back the chunk of file. Then in this one, you would just push it to the request buffer. So now this is the main function, the worker thread function. This one is quite complicated, but it's actually the most complicated out of everyone, but it's still not that difficult. But it's a while true loop. It's going to be an infinite loop. You would pop the messages from the queues and check for the message type. So you have to do, what you have to do is you have to cast it. You have to cast from the buffer. You would cast it from buffer. You would cast it to message type. And then you act on the message accordingly. So you have 3 if statements, if else statements. If it's data message, send pop message to the server, get back the result and push it to the response buffer, along with the patient number. So you have to create a way so that you can pair. You can have a pair of value. You have the patient number and the value, the data that is associated with the patient number, so that when the histogram thread function pop, it know what patient to update the histogram collection, because there you will display the number of patient, right? So file message, and that would be pushed to the response buffer. I will tell you at this point is that pair, there's a data structure given to you, or well, given to you in the standard library called pair. I tried that, it didn't work. What I had to do is I have to create a struct. I learned that from Gabe, another TA, is that you have to create a struct, and then you can cast it back into a char, because you have to cast it back into a char pointer so that you can push it to the response buffer. So by making a struct called, data patient data, you would be able to have the struct only contains two data value, a patient number and the data associated with it. So an integer and a double. So that should be simple. So the file message would send the pop message. So that if it's a file message, then sends pop message to the server, gets back the data chunk, and puts it in an appropriate position in the file. So that's it. While this data message, you have to push it to a response buffer. This one, you just immediately, you don't have to care about the response buffer. You will just push it directly into the file. So that simplifies this step. For this one, I want to say that in PA1, if you use OF stream for the PA1, that wouldn't work for PA2, because for PA3, because you have multiple threads sharing the same. I don't think OF stream works with multiple channels and multiple workers. I tried it and it didn't work. So you have to use open file, and then you would get a pointer to that file, and then you would move it around using fseek and using fwrite, fseek and fwrite. And then I think if you quit, and then actually in the past, one thing is, in the past, you used to be just, there's no response buffer. You would also do the same thing. You would call the histogram directly in the worker. But I think starting last semester, in fall 2021, they start doing this. When I took this class, there's no response buffer. But I think this is so they can, allow you to practice some more with the bounded buffer and all the threading. And then if you see the quit message, quit message, then you would send the quit message to the server to end the worker channel and break out of the loop. So this effectively end the thread, because the thread will be an infinite loop, and then you get out of it, it's done. How do you push the quit message? You have to manually. So inside, when you join down here, right? You have to join the threads after you create them. You would join them. Before you join the worker, you would push W amount of quit message into the request buffer, so that so that this and so that it can see it whenever it's done. So it can see it so that it know when to terminate itself. All the threads terminate itself whenever all the data is done. All the data is all the data is completed. Oh, and then histogram thread. All it does is it pops from response buffer, recast it as if you do it like I did, then you would just have pop it, recast it back into the struct, and then you would just update the histogram collection. Well, in this case, another problem comes up, is that what if what if how do you know, how does the histogram thread know when to terminate itself as well? Because it's also, I think it is another while loop. So the way you can do that is, one trick is, because the patient number can only go up from 0. So I think there's patient 0 to patient, I think 14 or something. Then if the struct contain, so that if you push data, the patient data struct, if you push in messages with the patient number of -1, right? Then you can see, then in the histogram thread, if it see that the patient data dot patient less than 0, then that means it is signaling the histogram thread to terminate. So it keep pushing things until it terminates. And I think this one I can show you that part. Hang on, before. Yeah. Oh, no. All that. So you can see, you just update and you break whenever quit signals right here. So that's how you would do it. Yeah. So yeah, you would just keep pushing it and then you come to terminate it at the end. And I think there's only one slide left. Yes. So the last thing is the main function. So mix the worker channels. It's like PA1 using a vector of channels. So make sure you can make a vector of channels and create threads. So you have patient threads, histogram threads, file thread, and worker threads. There's only a single file thread, by the way. So you don't have a lot. So you only need a single file thread to start generating file request, the file message. File data message request. And then you join the threads together. Before joining the threads, worker thread, make sure you push the quit message to the request buffer and find a way to terminate histogram threads. That's, I said, equivalent to quit message. What is one thing I want to say? Okay. When you, so for each thread, you will have the parameters. If you look at this, there will be parameters right here, or arguments. You want to make sure that, let's say you want to pass in the there's one error that people used to encounter a lot, is that you see that this request buffer right here, it's just an object, right? It's not a pointer. So when you pass it in, you might think, oh, let's pass by reference. Let's make this a reference in here, like the ampersand. Yeah. You can't do that. It wouldn't work, actually, and I don't 100% know why. But if you do that, it would yell at you, saying, it would yell at you a lot. It would yell at you for passing things around. Yeah, it would yell at you, and it would generate like very long error message. So the way you can do it is you actually pass by, you still reference it within here and make this you make the parameter a pointer parameter, and you would reference it within request buffer. So you would do an ampersand when you pass in the parameter, you would use a reference in here. So it would be an ampersand request buffer when you pass the parameter into the into the function call, into the thread calls. And yeah, I think that's the only thing that is particularly weird last semester that it took a while to debug. But that's I think that's it. All right, so that concludes our presentation. Any question for me? Does it make sense? I hope it makes sense. There's any clarification. Okay. So yeah, so if you have any questions, you can stay here. If not, I will stop the recording, and then I will be open for office hours until 11. So you can implement it now and then just ask me question, or you can, you can come back and ask question later. Stop sharing. So I will stop the recording for this one.